Today we have with us Thomas Tuloup, one of my close friends in Singapore and a French physicist who specializes in quantum computing.
Yes, well, thank you for having me here, MC. I am indeed finishing my thesis about condensed matter and quantum computing at NUS and the Center for Quantum Technologies.
So one of the reasons I invited you to the podcast is to share with us your abundant knowledge of physics, of astronomy, of everything else. But um, I want to start by learning more about who you are and share with my audience your journey through life. So why don't we start by you walk us through how you discovered your love or passion for science and physics, and how did that start in France and all the way to Singapore?
Yeah, well, that's a good question. To be honest, it started, I would say, quite early. It almost always been there. I would think I was always a bit of a nerd in the sense that I was interested in just understanding, figuring out how things work. Even I don't know, when I was like 6 or 7 years old, I was already like cutting little paper circles to represent the planet and gluing them to my ceiling to build a mini solar system in my room. And I guess it just like always kind of fascinated me, and it seemed quite logical, like through my education, to just pursue science, because it's a choice of career that not too many people frown upon. It's not like when you say, "Oh, I want to be a musician." Some people will have objections. Are you sure you can make a living out of this? If you say, "I want to be like a mathematician or an engineer," like people are usually gonna be like, "Oh, what a bright kid. That's a very good idea for your future." So I was I was quite always encouraged by everyone around me to just like pursue this mathematical career. At first, at first I wanted to be a mathematician because mathematics were like my favorite subject at first, because it was the one I was the best at, so it was easy to get good grades and please my parents. But but then I started to enjoy it for the sake of it. Just, at first a bit like a brain teaser in a way. It's like I just enjoy getting into like the thick of things, to understand like this, to consider like these complex systems, these complex problems, where you have to really like take some time for yourself and just trying to like slowly figure out what's going on. I guess, yeah, I just like the process of like slowly grinding through the details of anything. And um, and yeah, at first I wanted to be a mathematician for a very long time, because it was the more pure, the more abstract subject, where it was literally just, an intellectual journey. But yeah, it all changed when I got into École Polytechnique, where I got my first lecture about quantum physics. And it was wow, it was a revelation in a way, because it was a very complex and mathematical subject. So it was extremely satisfying, just from a day-to-day perspective, because the math were hard, where they were fascinating. And at the same time, it was math with a purpose, in a way that it was complicated math that was used to explain some of the most mind-blowing facts about nature, about the universe, that I've ever heard of in my life. So after the first few lectures, I was absolutely hooked. I was like, yeah, of course, like this is the kind of stuff I want to do later. I
Hmm.
want to I want to just like keep doing that stuff, because it's it's all the good flavor of math, of like actually using your brain to like its full extent, to really like crush hard problems. And at the
Hmm.
same time, it's actually discovering things about the real nature of things, and about the world that surrounds us.
I think we can all look back to our student days and point to the specific classes that really give us a spark. to lead us to discover what we're passionate about. But I think for most people, it just stops there. They just finish the class, get a good grade, then enjoy the intellectual fun, but then still look for something more practical in terms of pursuing an actual career in the job market. So, what led you to continue the education through a master degree, then a PhD degree? And I think a lot has to do with the present state of academia now, where the marginal the incremental research benefit has shrunk a lot compared to the early days. So what do you think is the point of doing something you're doing now in a primary science field, so deeply involved at the frontier of research?
Yeah, so I understand where you're going with that. Yeah, I mean, in a way, at first it was kind of a selfish choice. When I first went into this academic journey, I was not really thinking about what are the job market's prospects. Is my research really going to help? At first, it was mostly out of intellectual curiosity. I wanted to see just how far I could go. So for me, it was pretty logical. I, I wanted to see how far are we in physics. Like, what is the state of the art? And so what in the end, like, what's the extent of our knowledge currently? And for this, there was no other choice than going all the way through a PhD, because that's at this point that you actually get to the border of actual physics, and that you finally take your first steps into the unknown. And then there is indeed this realization that you're not going to do the same stuff as Newton or Einstein or Hawkins. You're not going to revolutionize science or physics in general, because like this kind of discoveries, they are one in a million. Like, no, very few people can like find nowadays that kind of like groundbreaking stuff that is going to completely change the way we look at one field of science. And instead you find yourself looking at like some much smaller projects, and with sometimes very narrow fields of application. But I guess when you look around yourself, you see that everyone is doing that basically. Like, I've never I mean, I've met a few people that have made significant contribution, but 98% of the people I work with, they are doing the same type of stuff as me. They're doing little progress, step by step, like in one very specific field. And you can think of it a bit like like a fractal, or like one of these like very complex geometric structure. Like, before we had like a circle of science, and we would expand it, bam, so suddenly we would like increase the diameter of our knowledge significantly. And now it feels like everyone is like at one point of this little circle, and it's just like digging a little bit more into the unknown. And it's not anymore a perfect circle, but everyone is like digging a bit its own way. And slowly but steadily, the overall body of knowledge that we all possess still increases. So I guess there is still satisfaction to be found in that.
Yeah, I think that's a great answer. It also relates to your reason of picking this career as well, as to expand the knowledge, the collective knowledge of human in regard to the world we are occupying in. We found ourselves occupying in.
Yeah, that's kind of like the noble endeavor, in a way, I try to fix myself, because at some point you have to ask yourself the question, okay, what am I going to do with my life? I need to put food on the table at some point. And I was, when you're considering job prospects, I might as well do something that I find satisfaction in doing so. And I believe that this choice of career, for me, it has like the double benefit of both providing me with whatever I need to actually live, and also giving me a somewhat sense of a greater purpose, I still feel like I'm contributing in a way. Many people have like a very very satisfying job when they can directly feel that they are contributing, right? That's not exclusive to research. Like I'm sure that when you're a nurse or something like that, you can very tangibly feel the benefits that you're providing for society in a way. And maybe that's like this idea of a greater purpose. It can probably help you go through like the a lot more difficult aspects of the job.
Yeah, I think I understand where you're coming from, but as the interview host, I have the duty to be the devil's advocate, or be the hard questionnaire, to push you a bit further. So my understanding of the current state of academia is you work through your grind, and a lot of it, whether your research leads to any result, depends on luck. And even for the ones who do, very few actually gets recognition in his or her field. So the reality is you work very hard for 5 years, but then you publish a paper that's only read a few times by very few people once, and then probably throw it out after that. So how do you reconcile that with your own subjective value system, value of the work you're putting in?
I mean,
So it may be something very meaningful to you, but objectively, not many people might care about what you're doing.
yeah, but it doesn't mean that the fact that many people care or not is not gonna change the fact that it can make a significant contribution to the world. In a sense, I don't know, when quantum mechanics was born in the 20th century, not many people understood what was going on, and I'm sure like a lot of them tried to do like try to figure out some unsuccessful ideas. But still, even if it was, I don't know, 50 people in the world that were a bit pushing into this direction, the consequences now are unimaginable. Everything, almost every field of physics now, uses quantum mechanics now. Even your phone, like the transistors in your phone, they're small enough for quantum mechanical effects to be felt. What I'm trying to say here is that yes, a lot of the academic contribution that we're going to get nowadays might be garbage. I mean that's a very rough word, but it's true that a lot of the papers that are published nowadays, they probably won't have a significant impact. But that might be, and I'm saying this by having a significant impact by themselves, because together with all these little papers, they still form a body of knowledge that together will probably contribute to actually make a breakthrough in a field. It's like for these 50 before, like we have these 50 not meaningless, but these 50 very narrow paper that try to like tackle a subject like from different angles, and finally some guy who has read all these 50 papers is going to be able to put all that stuff together to finally make a significant breakthrough.
I think what we're getting at here is basically how the knowledge progress over time, how knowledge generation works, how this knowledge production industry, if I may, how it works. And it's a lot of time it's not immediately apparent how an individual piece of output, what's the value of that, but it's over time, it's a collective unit of contributors that come together, and it might not be realized in the immediate term, but 10 years, 50 years, a decade, a century later, then you come about. If you have to describe the structure and the process of this knowledge industry,
it's like, in a way, like we are working ants in a way.
Yeah.
Like everyone is bringing a little crumb of knowledge to the hive, or I don't know how it's called for the hands in English,
Yeah.
but yeah, everyone is bringing like his little contribution, and someone out there will figure out how to make use of all that stuff, and yes, we don't have like we don't have researchers that are as popular in like pop culture as Einstein, for example.
Yeah.
But it doesn't mean we don't have like good researchers nowadays, and it doesn't mean we don't have significant breakthroughs that have been made regularly. We still get a Nobel Prize every year, and they're not given out of pity. Every year we get like a Nobel Prize in physics among many candidates, and it's for people that have actually showed some significant progress in physics. Like,
So why do you think then the physicists today that are making just as big of a contribution as Einstein and Newton, like back in the days, they're not getting the same level of recognition in the pop culture or even within university in the
it's
society today? Yeah.
it's more of a pop culture thing in a way. Like, for example, there are it's very funny, like, but it's just, I guess, it's actually not about the quality of the researcher, but it's just about the story that you can give to them in a way. It's like, I don't want to. I think Einstein is an incredible researcher, and he made like one of the, yeah, top 5, top 3 easily, like contribution to physics. But there were, even in his time, there were many researchers, many physicists that made just as big contributions to the field, and they are not the way they're talked about. It's not even close in terms of popularity. Like, I don't know, I'm thinking about like Pauli, I'm thinking about like Dirac, all these kind of, all these guys, they were genius, the same as Einstein. But for Einstein, I don't know there might be like a few explanations why he became like so prominent in pop culture. Maybe it was just his personality, his story, and it's a bit the same with Stephen Hawking, to be honest. For example, if Stephen Hawking wasn't disabled, if he wasn't suffering from his condition, I don't think he would have got the same recognition in pop culture. In a way, there are many people that are doing the same kind of very complicated math of like looking about black holes, or like making contribution to like string theories, and they are all they're all making like very good work. But what distinguished Stephen Hawking from the rest is that he managed to make the same extraordinary contribution while battling with like a terrible disease his whole life. And I mean, this is the kind of hero stories that you want to see. You want to see like in the media. It's a uphill battle, and it's like the triumph of brain over matter, or of whatever, right? So that's, yeah, that he kind of became like the in a way like the archetypal archetypal cerebral personage. Yeah.
So personally, if you have the choice, would you choose to be born in an earlier time in the world to be a physicist when there was more unknown and less known than today?
I think I'm very fine where I'm at, because
So you would rather be standing on the shoulders of giants with
Yeah.
what you're equipped with.
yeah, everyone was standing on the shoulders of giants in a way, except maybe the very first Greek philosophers. But Einstein, he was standing on the shoulders of Newton, for example. He managed to, yeah, in a way, he proved Newton wrong. Not really. He added like correction to the work on gravity that Newton had already done centuries before him. And just to come back on what you said about the unknown, right? There is still so much unknown these days, because it's a bit, you said that as if like in the time of Einstein, the universe was unknown, we had no idea what was going on, and everything was up for us to discover. And yes, many discoveries have been made, and it's been crazy this past century, but we still don't know shit. You will bleep the shit if you want, but yeah, it's like we still know nothing about what's going on. There is still so much stuff to discover, and of course it's not very well known in by the layman these years, because if you don't know what's to be found, how can you be excited about it? It's our job. I'm sure, like when people were trying to figure out, the black body radiation or stuff like that at the time, the common man at the time had no idea what was going on and was not interested one bit. And for them, physics was pretty much figured out already, right? Because the layman, he only knows about what we know right now, and all the little details, the little black dots that we have, like in our theories and stuff like that, that's usually where you can expect the next big thing to come out.
Do you think that the science and physics has progressed to a stage where the incremental knowledge production is becoming more and more difficult than before? Whereas, I mean, you in our prior conversations, you made a good analogy um, to to the back in the days when we didn't have satellites, how you don't know the full spectrum of the Earth, and you might chance upon a new continent just by sailing away on a random day to a direction. Whereas today it's much harder to discover something that's not already there. Do you feel like the work you're doing now is a lot more challenging than back in the days, let's say 100 years ago, or with more tools at hands, with more computing technologies, collaboration, interdisciplinary industry? This whole industry is working more efficiently now for you. Is it more difficult or easier?
I don't want to complain, but I would tend to think that, yeah, in some aspects it's a bit more difficult, because the field of physics keeps increasing, right? And in a way, it's like all the stuff that is easy to find has already been found out. In a way, it's like the the complexity of physics is growing faster than our intellectual capabilities. In a way, it's like I think people 1 century ago, they were just as clever, just as smart, just as ingenious as us right now. I don't think like like the just mankind can significantly evolve in its like intellectual capabilities over 100 years. So we probably are given the same amount of reasoning capabilities our predecessors, except that right now the complexity of physics keeps adding up, in a way, and that's why research becomes right now so much more fragmented, because 400 years ago, 300 years ago, it was still possible to have a state-of-the-art understanding of mathematics, of physics, of biology, all in the same place, all in the same brain. We had like some many scientists like Descartes that had time to do physics, mathematics, philosophy, all the same, and they were pioneers in all these fields. And I don't think that Descartes was more of a genius than Einstein, for example, but it's just that that progress had not been made before, and now it's just getting harder and harder to find places where we actually have the capabilities to make a better contribution. Of course, technology improves, so in terms of experiment, like we have more and more experimental capabilities, but yeah, just in terms of the state of knowledge, the issue is that we are getting more and more specialized. In a way, it's hard right now to have almost impossible to have a perfect understanding of everything that's going on in physics right now. Everyone has to specialize at some point, because no one has has the brain necessary to take all the entirety of astrophysics plus the entirety of condensed matter plus the entirety of I don't know, string theory. You cannot. No one knows all that stuff at once.
So to tie the last two questions together, you're saying now knowledge production is more difficult, but you still rather living in today than before. So seems like you're up for the challenge, and you would rather um, live through the grind than
Yeah, yeah,
the easy life back.
yeah,
And not saying Einstein had a
no,
easier
no,
life.
of course not. Like, because he still, I mean, that, and that's why he made like such great contribution, because he used like all his intellect to make like all these progresses.
Yeah.
But yeah, in a way, it's, yes, I'm not afraid of the challenge. I'm seeking a challenge. That's why I'm doing physics, because I want to grind my gears.
Yeah.
I want to be tackling these complex systems. That's the whole interest of it. Like,
Yeah.
if it's just to do like simple additions or whatever, I don't know. Like, I could find many other jobs where I can just do like simple math, in a way.
So yeah, I think that's a great segue to our next question. Just more fundamentally to you, what drives you, what motivates you, what gets you up every morning to do what you do, given that you said you're seeking the challenge. So where does the motivation come from? Perhaps my guess is, who are the physicists that you look up to? Perhaps they might be a role model for you.
So yeah, for this role model question, I mean, there are many physicists whose work I admire, right? Like, I don't know. I'm thinking of Richard Feynman, for example, whose capability to turn complex problems into simpler ones is something that I absolutely admire, because I feel like, yeah, that's a skill that I thrive to develop, in a way. Um, and yeah, he made like just for his life story, he has very interesting life stories with like a lot of stuff going on during like the research, for the atomic bomb, or later the Cold War. So yeah, his life story is pretty cool. He made like some very interesting contribution to, I mean, and that's saying it lightly, right? He made like some tremendous contributions to the field of quantum mechanics, quantum physics in general. And yeah, so of course I admire his research, I admire his methodology, and he has a cool life story full of anecdotes to add to that. But I'm a bit wary of idolizing any researcher. So I wouldn't take like a full person as my role model, right? Because like this Richard Feynman guy, like, if you look it up, there are many things that are going to like put stains on the whole picture, because like I think his attitude in life with women in general was actually quite dubious. And many people have, if you look up into the light of, if you scrutinize the life of every single public figure, like celebrities, and physicists are not exempt, you will find some dirt
Yeah,
somewhere.
that generally I agree as well. As I think our society tend to idolize people too much, but every person has different dimensions. An actor, he could be a great actor, but off the stage he might have personality defects. So even politicians, every human being has both the the flawed side, and also the aspect of them that should be celebrated. So I think that's a fine point. Um, so that apart, what drives you? You think where does that come from? Is it just the innate curiosity, or do you ever see that runs out someday?
It's a combination of both. I think you need two things to be able to like keep up in that kind of life. It's you need like a greater purpose, something when you're like actually like stopping, asking yourself the big questions, like, what am I doing with my life? Am I content with what's happening right now? And this is a bit like the intellectual curiosity. It's I'm very fine with my purpose on Earth being to provide, to increase the body of knowledge of humanity, because it's a journey that I personally enjoy. It's something that motivates me. I want to understand what's going on, in a way. And the thing is, this larger purpose, it's not the thing that can for me at least, it might not be enough to keep yourself going on a day-to-day basis, because sometimes you just like you get caught up in the grind and you have like so much stuff to do everywhere, and you don't have time to think about I'm contributing to science, this is all gonna be great. So that's why you also need the second component, that is you need to enjoy what you are doing on a daily basis, just like the little details, the groundwork, the footwork. And that stuff, it's also something I enjoy, because as I said, it's like some people, they do sudoku to distract themselves as a hobby, right? Not my thing. But for example, actually solving these like complex equations and considering this complex problem and just like blocking on them for 5 days straight, and until like what night at 3 a.m. you have the illumination, and you spend like 3 hours until like you see the sun rising, and you're barely done like writing the solution you just figured out. This is, for me, this is a very high kind of high to ride. And this, so I enjoy doing this also, in some aspects of physics, and I think that's kind of what determined my career choice. More specifically, the field I chose to go into, because it just why quantum computing? Because the math is the coolest for me, to be honest. I find other fields of physics equally fascinating. I think hearing about astrophysics it's an incredible subject, one of the most like pictorially cool that you can think of. And I did some astrophysics at some point, but the math wasn't as cool. The day to day was not as exciting for me as quantum computing. So I switched, even though I have boundless love for astrophysics. But it's not something that I can see myself do on a daily basis.
That's very interesting how you formalize it, like almost as a theory of how to find your passions. You have two points. One is you got to see it fit within your greater purpose, but also second part is on the day-to-day basis, that the work has to be enjoyable, and how you make the distinction between the astrophysics and also quantum computing. The latter is obviously more interesting because of the math and the day-to-day.
Yeah.
So,
and for me, right, I'm sure many people, they find the math of astrophysics the best, and that's maybe why they do that.
Yeah. So I think overall so far we had a good grasp of your background and your general views on academia and your career choice. So, and now I want to make a switch to something more topical, more subject area specific, which is your, let's say, your side passion outside of quantum computing.
Side geek. Yeah.
Your side geek, and which I also think is a very fitting topic for the first episode of the podcast, which is the beginning of the universe, if I may put it that way. Right. So please, Thomas, like educate us on how we got to here where we are today. Two men sitting in a podcast studio.
Yeah, that's a big question, right? Big question, not solved. But I think one cool story I can like tell you about to take you a bit through this process is about like it's a very very poetic phrase from like Carl Sagan, I think, that said that basically we are all stardust contemplating the stars and wondering what they are, in a way.
We're all stardust contemplating the stars.
Yeah. And this is actually, it's not just it's just, we're not just like stardust to be, it's not a saying to be cool and poetic, right? We are actually factually stardust.
It's factually accurate.
Yeah. And it's one of the, I know it's one of the most like mind-blowing discoveries that I had in my astrophysics journey, right? It's basically it's tied to like the creation of the universe, right? Of like everything you see around you, because I'm not going to go through like the actual details of like the very first seconds of the Big Bang, because this can it's like 5 hours of lectures just for the first 1 second of what's happening, right? But basically, I will just summarize that stuff in, for reason unknown, something happened, and the universe that was originally a singularity started to like suddenly expand. Started to suddenly like came to life, to expand in a way, by creating and basically all the energy that was contained in singularity took form to form what we know nowadays as the very first elements. Basically, at first you had only energy, and then you had like the very first subatomic particles like quarks, and then you had like stuff that stuff finally managed to like recombine into some protons and neutrons and electrons that are like the building block of the elements, the atoms, and um, and and then these protons and electrons they fused together in a way. I mean, to form like the simplest element that you can find in the universe, that is hydrogen, and that still to this day probably represent, I think it's like 75% of the universe is made of hydrogen, of the known universe. And yeah, and we had like 25% of helium. And basically, I'm gonna start the story here for the purpose of the stars, because yeah, that's what happened after the Big Bang. That we had like this very this universe that is basically just a very big cloud of very very diffuse gas in a way, with mostly hydrogen, a bit of helium.
Now, how long ago was that from
So
today?
so basically the Big Bang happened 13.8 billion years before now.
So Big Bang is the beginning of everything.
It's the beginning of space-time as we know it,
Okay, so
in a way.
after the Big Bang, we have the dimensions we have today. Is the
Yeah,
space time.
yeah, kind of. You can think of it as that. In a way, there's like you might not, maybe you know, maybe you don't, that like the universe is expanding still to this day. And it's basically the 13.8 billion years that we have. How did we figure this out? It's very simple. It just we measured like the speed right now at which the universe is expanding, and we just went back in time. We just ran the equation the other way around to see like the evolution of the expansion of the universe, but the other way, but going back in time. And so of course, so that means, like the compression. And if you just follow the mathematical curve, you come to a point where 13.8 billion years before in time, the overall like metric, the overall size of the universe was basically zero. And of course, the thing is, this is at some point, there is still a lot of assumptions, a lot of unknown. We are pretty sure of what went on after the first nanosecond. We are pretty sure, like 1 nanosecond after the Big Bang, we have pretty good models that can probably predict more or less what happened at that point. But the first nanosecond, we have no idea,
Yeah,
because all the laws of like quantum mechanics, general relativity as we know it, they cease to function in a universe that is the size of a tennis ball or whatever.
yeah. I think that goes back to a fundamental paradox or problem in philosophies, which is how do you get something from nothing? Is that the first question of everything?
Mm. Yeah, and it's of course it's like one question that I would be so happy to know the answer to, right? Is like, why is there something? And it's something right now, it's outside of our capabilities,
Yeah.
right, to understand what's going on into the 1 nanosecond. And we can only like speculate of what we are going to find, if we ever find something. because let's imagine that we find a way to figure out a bit like how this stuff works at this scale by like some significant breakthrough. And what doesn't tell us that okay, we're gonna push the thing back. No, it's not 1 nanosecond, but no, we know everything until 1 billionth of a nanosecond, and then after that we still know nothing. So
it's the idea of the limit where it never approaches zero, but
are we
can
ever
go
going to
infinitely
figure this out?
close to zero. But it's just, how did it start from zero to something bigger than zero? That's a part we're missing. But today we're focusing on the latter part.
Yeah, correct.
That's more interesting thing and more
so let's not
knowable
digress.
things to talk about. So we can go back to the formation of elements on the
correct. Yeah, let's go back
the
to
hydrogen,
the cloud of gas, right?
Yeah.
So basically, after all this stuff happened, you had like the universe that was made basically of diffuse cloud of hydrogen and a bit of helium, and basically this gas, now that it's standing there, it's only it's only feeling one of the major interaction, that is the one everyone knows, gravity. And gravity is just the fact that two bodies with a mass, they attract each other in a way. So of course, if you're a particle floating in space, the only other thing that is out there attracting you is the other particles. So naturally, very slowly, because these atoms, they are super light, so the interaction is very weak. So it's gonna take hundreds of thousands of years for the cloud to actually become a bit more dense. But there was nothing in the universe, so it had time, right? Nothing else was happening anyways. So this gas, it's very slowly started to like concentrate over itself, and basically there was really nothing stopping it, right? It was just gravity. So you can picture that this kind of glass, they get more and more dense, until more or less, because of like the natural symmetry of gravity, they usually took the form of like more or less spheric forms, and this cloud of gas, they start to like basically collapse on each other. And what happens is that when you compress a gas, it actually heats up. It's thermodynamics. It's a basic thermodynamics. It's like when you pump a basketball, if you go a bit too strong, you notice that the tube that you're holding is actually heating up, and it's simply because compressing gas heats up heats it up. So basically, we have this cloud of gas that gets like more and more dense, and so the gas that is at the center of the cloud is getting like much more compressed than the one that you get on the in the periphery of it, and the temperature is going to rise. And what happens at some point when because nothing is stopping gravity until at some point the temperature and the pressure inside the core of what's going to be the star becomes so high that basically these protons, electrons, these hydrogen atoms, they are pushed against each other so hard that they can like basically break all the potential barriers, all the natural repulsive laws of nature that you can get between these two atoms, to actually have their nucleus fusion in a way. Like this is literally what's called thermonuclear fusion. This is the process that physicists nowadays are trying to mimic to get a potentially nearly infinite source of energy, maybe the most efficient that we could have. And basically that's how a star is born. It's just you compress gas really hard until the protons that are inside its core have no choice but to fusion into heavier elements. And so I would say most of the stars that we observe in the galaxy these days, the sun included, are actually thermonuclear reactors floating in space. In a way, it's like we have this cloud of gas, and inside of it, only in the core, when the pressure and the temperature is enormous, you constantly get these hydrogen that are getting like fusioned into through a complicated process that are getting fusioned into helium. And what happens when you do this thermonuclear fusion is that you release an enormous amount of energy in a way, and through radiation. Basically, this is the light that we get from the sun. Basically, all this UV light and stuff like that, and these radiations are so important then they actually manage to counteract the effect of gravity that wants to make the cloud of gas collapse on itself, and that's how you get basically this stability. That's how you get like the star having like a more or less definite shape into space in a way. And
So at the beginning, they were just two clouds of dust, of two clouds of gas,
yeah,
and
one
they fused together, and the nuclear reaction happened.
Yeah.
And then the force was so strong that it counteracted the gravity.
Yeah.
So it was expanding. It was going the other way.
Yeah, basically, it's like it's finding the balance, right? It's as if like it's like there is just one strength, gravity, that want to like push everything in, and there is an opposite force coming from the nuclear reaction that wants to push everything out. And basically, it turns out that you get this right balance, and that's what's gonna fix the
shape of
the shape of the
star. Like Earth, for example, that's why Earth is this round globe that we're seeing now.
Earth is not a star, right? It's more, you mean the sun, probably, right?
The sun, okay.
The sun, yeah.
Okay.
Because no thermonuclear fusion going on inside the Earth.
Okay, so I mean, I am a layman, complete layman.
Yeah,
so
yeah.
there we go. That clarified. So that's the birth of a star like the sun.
Yeah, correct.
How come there are multiple of them?
So I mean,
were they all created at once?
So the creation of stars, no, they were not all created at once. There was probably a first star ever created in the universe. I don't know where, but honestly, why we got like this dispersion of stars? It's all down to chance. It's like this basically the repartition of the gas into the universe at very first. It was not perfectly homogeneous. Why? We don't know. But that's this repartition of gas in the that's everything came from that. It was not perfectly regular, right? There were some points where there was a bit more gas, so the gas around it would naturally go to like these heavier concentration points because they are heavier, and so slowly but steadily you would get like clusters of like gas that would like pop out a bit. Like the less dense region, they would become even less dense because the gas would like migrate toward the already more dense region, because there was a bit of imbalance at the very beginning. We don't know why. Don't ask me why. I don't know.
So that's why we had multiple stars.
Yeah,
because this process happened at different places that created them.
And actually, it's like that's why we have like different galaxies in a way, right? Because stars, they exist in a galaxy, and there are like at least billions of galaxies. I think it's
so what is a galaxy then?
A galaxy, it's basically a large group of stars in a way. It's a structure. It's at first all these clouds basically they just dispatched themselves into like smaller clouds, and these smaller clouds, they became galaxies at first, because each smaller cloud you get like some each smaller cloud, they become into even like smaller clouds basically, and inside you get like, and inside the star creation process happens. Basically it's like a galaxy. It's just a very large concentration around same like hundreds of billions of stars in a galaxy.
Okay, so at the beginning there were stars. There were multiple stars, multiple galaxies.
Yeah, basically multiple galaxies, each containing multiple stars. And by multiple, I mean a lot.
Okay, so where do we go from there then? Are you going to zoom in to talk about the sun, or for example, the galaxy we're in?
I could do this, yeah, because let's talk about the sun for a while, and then I will tell you about this whole stardust thing. Because basically this is right now, that's where we at. This whole like thermonuclear reactor in space, that's the sun. Basically, that's what the sun is doing. That's what it has been doing for 4.5 billion years. That's the age of the sun in a way. And basically, this is not going to last forever because it's a very big cloud of hydrogen, but there is a finite reserve of hydrogen, right? Because the thermonuclear reaction that's happening is that hydrogen is getting transformed into helium in the end. And so as you do so, of course, you consume the hydrogen, so you have more and more helium, less and less hydrogen. So at some point, what's going to happen is that you won't have enough pressure inside because you will have the core of helium and you won't have enough pressure around this helium core to fuse more to make the fusion of more hydrogen. So at some point, the thermonuclear reaction will stop. This is bad for us, right? Because what basically there will be like a little subtlety of what's going to happen. It's going to happen in 5 billion years, something like that, 4 or 5 billion years. But at some point, the reaction will stop. So we'll have a bit of like a micro collapse because nothing is going to counteract the gravity anymore. So it's back to collapsing. And you will actually have a little fight for life of the sun because of this collapse. The collapse is quite violent, so it will be enough for a while to reignite the reaction. So it's as if like you will have your reaction and then it's gonna stop just to say like a bit more one last time, like wait,
Yep.
I have still some fight in me, in a way.
Yep.
And that's what we call the red giant phase. That's actually a star in the end of its life. It's doing a last one run of fusion. The sun is going to increase in size. The diameter is going to increase by 200 times 200.
That's when it becomes a
red giant.
A red
it's
giant.
Called, a red giant. This is, I think, it's gonna last a few more billion years.
And that's when Earth will be.
Yeah, we will be
devoured
cooked
by the red giant.
It's Mercury and Venus will be devoured. Earth, I think at first it's a bit hard to tell because, as you can imagine, this kind of reaction is gonna perturbate the whole orbits of the planet. So maybe we're gonna be centering, maybe we're gonna crash into the sun. I think at some point we're gonna crash into the sun. That's what's going to happen. But if you want to know, actually, life on Earth, it probably has only 1 billion years left, even before all this stuff happens. Why? Because
and this stuff happens, you said how many billion years?
Basically the red giant phase, you can think 5 billion years.
5 billion years away. So okay, then the life on Earth will end a long time before that happens.
Yeah,
so,
exactly. Even just because of the sun, because as it starts to like to run out of hydrogen, it starts consuming. Because the questions are a bit complicated, but basically the sun is gonna it's getting slightly bigger and slightly more luminous, setting like slightly more power as it goes on. This is because of the that's just the laws of physics, right? That tell you that. And what's going to happen is that in 1 billion year, the power that we will get from the sun will be increased by 10%, basically. And you're going to tell me that's not a big deal. The problem is like that's enough so that the atmosphere won't be able to retain the evaporated water, in a way. So all the water that evaporates, it won't stay in the atmosphere to form clouds, to form rain, to go down later. It's gonna go into space. So we're going to be losing water at this point after 1 billion years. So it's going to be it will be the start of
so
things.
That's why there's an endpoint to life on Earth, is because sun is expanding.
That's one of the possibilities. I don't know which one is the first one. I don't know which one is going to happen first. There are many reasons that.
So why then can we segue into that? Have a small digression. Why there's an endpoint to life on Earth?
Yeah,
I understand the resources are finite.
Oh,
and
yeah.
If you assume the current trajectory will have more and more people.
Oh yes, but this is even, I think there is many threats for life on Earth on a much smaller time scale, right? That this astrophysics stuff. 1 billion year, it's gigantic, right?
How long has there been life on Earth? Just to put in in the scale?
That's a good question. I think it's like I'm not a biologist, right? So I'm not 100% sure, but it's at least hundreds of millions
Okay.
of years,
So it
right?
seems like we're
But
about halfway.
yeah, in a way, we are probably like a bit before half, and after that, it's going to start to be very nasty here because we will be losing water, and water is just essential. So yeah, better start to hurry up.
Losing
Fine.
water because the
Because
sun
because
is heating up.
yeah, because the sun's gonna heating up, so it's gonna damage the atmosphere, and the atmosphere won't be able to retain the water that evaporates.
So the water will the water we see now as clouds will keep flowing into the universe.
Yeah, in a way, yeah, because we will have like the ozone layer is
Yeah.
going to be damaged in a way, and it's all downhill from there. Yeah, so and even and so yeah, it's like this is 1 billion years. Like I think 3 or 4 billion years. It's the luminosity will be 40% more, and it's enough to evaporate water. Basically, it will be unlivable. Like the water in the ocean will literally evaporate.
So if you have to put a bet on that, do you think before the time reaches we'll find an alternative living space
I mean,
for human?
at this point, the only alternative is like finding a new planet, right? Finding a new home to colonize, and I don't know how we will do that if we ever do.
Nobody will know, and I think a lot of people are working on that. A lot of smart people are working on that.
Yeah, but you see like how difficult it is to go to Mars, and Mars is probably not the ideal candidate to start life, because the moment the sun dies, Mars it's over also. So
it's just a temporary solution to postpone the problem. Eventually
and
occur.
It's not probably not postponing by much.
So it seems like our destiny's fixed.
If it is to continue, it will be outside of the solar system. That's for sure.
So to another
star. We need to find another planet. I don't know. We can try. I think it's called Proxima Centauris. It's the closest star that we have from the solar system. The problem is it's 4.2 light years away from the sun. So that means that if you're traveling at the speed of light, it's gonna take 4 years to get there on our whatever spaceship that we have.
But does the time and speed functions in the same way as in the sun's solar system? Do you think there's some cheat code we can apply, and then all of a sudden we're
there? If there is a cheat code, no one has found it yet. In a way, we have never managed to make anything travel faster than the speed of light. Yeah.
Okay.
So this is, for me, like, this is all speculative, right? Like, after, I don't know, like, it would like literally break one of the most important law of physics if we manage to do that. So I mean, honestly, if we manage to get something to fly in space at near the speed of light, that's already incredible. We are not even there. We are so far from there because there are many constraints. The amount of energy would be colossal.
Got it. So it seems like we're in this temporary phase of the universe that allowed humans as a species to emerge, life on Earth to emerge. And the destiny is there, and then we're just
it's like when you think of it, the window is not that big, right? Because in the first like few billion years of the solar system, the surface of Earth, it was perpetually like bombarded by debris, like asteroids or whatever floating space object. And because at first it was not stabilized in a way, so it was everywhere, it was constantly crashing on Earth. So the surface of the Earth was literally in fusion. It was literally melting because of the impact of the asteroids. So that's not a livable condition, right? So it's only after it's stabilized that we manage to like get the liquid water, and we have the little miracle of bacteria that start to develop in the water into life as we know it. So the window is not that big, right? Maybe, I don't know, maybe the window was like 3 billion years for between the first possibility for life and the end of the possibility for life.
It's 3 billion years on the spectrum of how long from the beginning of
Because
Earth to
because I
the
mean
red
Earth,
giant?
it can this stuff is about the same lifespan as the sun, and it's 10 billion years.
10 billion.
Right.
So
in
the
10 billion
window
years,
is about
you have like a 3 billion year window. Yeah.
so 3 billion out of 10 billion years
Yeah.
that we're here. That puts things into perspective.
Yeah. Yeah. It's
Right.
all very temporary, right? When you
Yeah.
look at that stuff. But
and it's not to mention how short our lifespan is
yeah,
for each person.
so in a way, that's
In
why
that
you
3
can
billion.
also tell yourself that this is not your problem, right? In
Yeah.
a way, this is not going to be your problem. So
Yeah.
might as well enjoy the ride.
Yep. I think we got carried away a little, but I feel like we've gotten a pretty good understanding of from the beginning to where we're going. But
Yeah.
I feel like you did have something
Yeah.
prepared to
Yeah, I
share
mean,
more about in the middle. I just cut you off.
Then let me just
Yeah.
finish that stuff real quick, right? I'm going to go very fast. It's simply that, yeah, basically I describe, what happened to the sun, what happened to like the red giant phase, the death of the sun. It's not the same for all stars. Basically, that's where I'm going, because basically what happened in this red giant phase is that because of the condition of like temperature and pressure, it's always the same, like inside the core. You can actually launch sometimes some fusion of some other heavier elements. Basically, I said like hydrogen could become helium, but you can go a bit further down like the periodic table. You can after that helium, you can make like fusion to create like, I don't know, like carbon, oxygen. It can go even as far as neon, magnesium, yeah, this kind of stuff. And so this is basically how all the elements that we know on the periodic table up to uranium, right? That's how all of them are being created. In a way, it's like these stars, they're like the main factory to create like these elements. This is the case until the element of iron, that is like the more stable element in the periodic table. What I mean by that is that in a normal star, right, even the biggest, the heaviest, the more like productive one, they can go all the way to create iron. Right, but iron is like number 26 out of 94 elements, so there is still a whole lot of elements that are everywhere now: copper, zinc, gold, lead, platinum, all that stuff. Right, it cannot be created by the stars in their fusion. So how do we get these? This is thanks to one of the most beautiful and cataclysmic event that you can watch in the galaxy, that are called supernova. Basically, this is what happens. This is the fate of the biggest stars, the one that burn the brightest and live the shortest. And basically, at some point, once you are finished burning not burning, producing iron through thermonuclear fusion, at some point you're out of comburant and you're out of fuel, and you have this core of iron, a solid ball of iron in the center of your star, and suddenly, the energy turns off. No more power, right? No more power to expand. So you can imagine a cloud of iron, in a way, that is suddenly collapsing onto itself, right? Until it becomes like a ball the size of half of Singapore, 20-kilometer diameter. And so it becomes like this and becomes tiny. So then everything that is the rest of the star, all the gas that is outside of the star, in a very like cartoonish manner, when they walk over like a cliff and nothing under my feet, they realize there is nothing. So it all starts collapsing it all starts collapsing very fast until it meets this like tiny ball of super 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 compressed iron. And basically this cloud is going to rebound, to smash against this iron core and rebound. And this phenomena, it gives rise to the most cataclysmic explosion that you can think of. That's called a supernova. To give you an idea of the scale of a supernova, in the year 1054 on planet Earth, there was an event that was documented by many scientists, mostly in Arabia, like Arabia, China, Japan, where people were actually doing science, because Europe, people were busy like murdering each other. So people that were paying attention, they noticed, like we have many proofs in like written books. They all say at the same times, approximately, a second star is born in the sky. And I think basically they're saying that it's like as bright as the sun. So literally a second sun appeared in the sky, and for them, and apparently it lasted 23 days. I think 23 days. For 23 days, the guys documented like what's going on. Is it like they were all, oh, this is bad omen, this is good omen. They saw a second sun, and so it was visible by day for 23 days, and by night for 20 months, something like that.
So there weren't a night on Earth because there are two suns.
Oh, maybe. Yeah, probably. Yeah. Yeah. It was probably like full daylight, full sun for like 23 days. So I'm sure many people thought it was the end of the world, right? And what was that stuff? It was a supernova in our galaxy. Basically, that's what happened when it's so cataclysmic that you see a supernova in a galaxy, you will see like that stuff for days. It's gonna be so bright. The time it's like dispersed. That's for days you're gonna have like a second sun in your field of view. And
So are you saying that's another endpoint for a star?
For a star, yeah.
Other than red giant, that could be an alternative.
Yeah, it's like one of the possible fates. Basically, depending on their size, all stars, they don't know the same fate. In a way, the sun, it's on a smaller scale, so it's less spectacular. After it's done, burning everything, it's just gonna be like slowly disperse all its element into the sky, into the space, until there will be only a bit of like a dead core remaining. That's what we call a white dwarf, and it's probably going to stay there, waiting for the end of the universe. Nothing too spectacular in a way, but when you have like very big stars, we get like this supernova kind of stuff. And where am I going with that? Is that the supernova, it's so violent, the energies that are like involved in there are so important that it's enough to actually force the thermonuclear fusion of all the elements above iron, in a way. So everything, copper, silver, I think it's after iron also, gold, lead, platinum, uranium, all these heavier elements, they are all they can only be created from a supernova event. So it has many interesting consequences, because here on Earth, we have copper, we have gold, we have lead, right? Inside Earth. So what does it mean? It means that
it came from somewhere. Exactly. It came from another supernova.
Exactly. Like probably the materials that are like building Earth, it's probably clearly some of it comes from a supernova. So there was very likely a supernova before us, right? That blew up, and to create maybe the sun, the solar system, us. So in a way, we already we are built from like the remnant of a star that already blew up.
So you're saying before sun there was another star that had a supernova event.
Maybe it's
that give the sun the elements that we have on Earth today. Did we get these elements from the sun, or
no? Exactly, yes. we got them from somewhere else, because the sun it right now it's only manufacturing helium.
Yeah.
Right. So that's not from the sun. That's from the supernova that was before us, in a way. And I'm not sure if the sun is like kind of like the second generation star, in a way, because like you get this stuff blow up, and then it's all gas, so probably a lot of hydrogen also.
Are you saying the Earth is older than the sun then, in that case?
I mean, depends. The Earth as we know it, no, it's not older by the sun. It all was created about the same time.
But Earth has elements that the sun is not producing, so that means it came from.
Yes, but it's possible that the sun was created from the same supernova, I think, than Earth. Basically, we had like the supernova, everything blew up because it, of course, it creates some of the elements, but still it's quite rare, right? Most of it is still going to be hydrogen. So it's likely that like a lot of like the hydrogen went back, it dispersed and then nothing to do. So it's just gonna come back into another one and it's gonna go for another round, basically. And it's gonna create the sun. Like it's possible, I think the sun it might be like a second generation star in a way. Right? It's like the stars, they blow up, and then with the star that is blown up, you can make another star. In a way, right? Stars are constantly being created. Right now, you can like watch the sky, and you can find some places that are called like the nebulae, that are literally the birthplace of stars. They are huge cloud of gas that probably come from some sort of cataclysmic event in the past, or maybe they were just there and taking their time. I don't know. And then from this cloud of gas, you will get like some bright points coming out that are like the stars that are being born in there.
The star like the sun.
The stars like the sun.
And does every star has planets revolving around it?
Not every, probably not everyone. It's probably likely that a lot of them have. Yeah.
And what determines the planets around the stars?
I guess it's what. No, you're raising like a good question that I'm not sure of, because it feels like planets, they're made of like mostly I mean the rocks and the stuff like that compose them. It's probably like some heavier elements.
So it seems
right?
like they came from the same event that created the stars.
Yeah, I think maybe the very first stars that didn't have planets because there was nothing to build them. Like because Earth, you have like iron, you have like everything, all the rocks, all the minerals that are inside. It's all heavier elements. It's not hydrogen and helium, right? It's heavier elements. So maybe to have planets, you need to have like supernovas before. Yeah, maybe there was no planet before the first supernova. That's something. That's my understanding of thing would say that. Maybe I'm wrong. So
let's say there was a supernova and it created the sun and the earth.
Yeah.
And the sun is slowly becoming a red giant.
Yeah.
And that's the in phase. But I think you're pointing out that the fact that planets like Earth being devoured by sun might not be the only alternative ending.
Yeah, and basically, and to come back to like the stardust thing, the whole thing that I was also trying to say is that there was something before us, right? There was something before Earth, before the sun. Like the elements that build us, they were like created in a star blowing up before, even, right? Like before the solar system, there was something else that blew up, and that is now become like recombining again, this time into the solar system. And who knows what's going to happen next, right? Maybe we'll forever be like this, the sun will forever be this white dwarf, or maybe at some point it's gonna collide into something, it's gonna get swallowed by a black hole, or two galaxies are going to like collide. That's also a possibility. Like our galaxy is actually moving towards another galaxy. So at some point, these two galaxies are going to merge, and a lot of things is going to happen.
And that will happen after the end of sun,
I think so. Yeah.
So let's say after the end of sun, what could cause Earth to continue its life?
I mean, Earth, it will probably just be like a piece of calcinated rock and will be dispersed in a way. Because at some point, before the end of the sun, I think the Earth is going to like collapse into the sun.
Okay.
And from then it's game over. It's gonna be like fused, like decomposed into elementary particles and evaporate.
So it will never be a state where the Earth retains the shape as it is today after the end of sun.
No.
So the end of sun means
of
the end of Earth,
yeah,
as we know it today.
Yeah.
It's just we become part of the sun.
Yeah, we get like literally burnt into the sun, and and
so that fate is inescapable
unless you have like very big reactors to attach to the Earth to fly away. But yeah,
very big reactor to push us away from the sun to escape.
I'm not sure if it's physically
Okay.
possible, but I mean, one
So
thing is
just
for
tie
sure is
back
that
to the
if we don't move the Earth, that's what's going to happen, right? So the only possibility to preserve Earth is to get out of the way. In a way.
So then to tie back to the supernova you introduced just now, what was the point there? What were you trying to get to?
I
Bring
was
in the supernova. You're saying that there was something happened before the sun. That
basically I was it was a way to say that there was something before us, right? We are not
Yeah.
it's like we are not just like straight off the Big Bang in a way, right? It's like we have literally pieces of stars inside us, right? Like everything that built us was created in a star before.
And you're saying the same thing could happen after.
And I'm saying that it's like it's in a way it's all like kind of like cyclical in a way. It's like after we are gone, right? Like that stuff. Like even you can see even on Earth, right? You can like you can plant a tree wherever you are buried, and your components are going to like go.
Reincarnation,
Yeah,
the idea.
you're gonna go somewhere else, right? And then even after Earth is like burned into the sun, in a way it's not the end. The atoms are still going to be there and it's going to be dispersed. Maybe you will go into like solar system, and we'll go in another and we'll part way there. I don't know.
So that might be the end of our friendship when I
that will make the commute a bit harder.
or travel to different solar systems.
Yeah.
Well, on that depressing thought, we can wrap up our first episode. I think it's been a pleasure to speak to you, Thomas, and very interesting. And I'm sure we'll bring you back on at some point later.
Yeah.
To share more about your actual expertise in quantum computing.